is a very old structure, excuse me, and there are some limitation to this particular data structure. We'll discuss about this, like spaghetti structure, whole polygon structure, points and polygon structure, and topological structure. Now if you see a spaghetti model, now here you have a collection of coordinate strings with no inherent structure. With no inherent structure means it does not have any spatial relationships attached to it. So it doesn't know what is on the left hand side, what is on the right hand side, what is the starting node, ending node, and what is the size of a polygon or an area. That's why making a coordinate, storing a coordinate string is not a very important thing. The only important thing is how you can retrieve a data at one point of time. So it does not have any inherent structure. So you can see that point, it will have a coordinate pair, a line will have a coordinate pair, and a polygon will have a coordinate pair. So this is a simple closed loop. And there are so many things, like if you see this particular arc, this will be stored twice. One will be stored at 33 and another will be stored at 39. So this particular string is not being shared by this polygon and this polygon. But so that is the limitation of a spaghetti model. So spaghetti model is usually derived from manual digitizing. Crossing lines means no crossing node. Now if there are two lines which are which cross to each other, as per the topological structure, it should have a node between, but in this there are no crossing nodes. So that is one of the limitation. Then common boundary between adjacent polygons is recorded twice. Like I was giving you an earlier example that this polygon, this particular this boundary will be stored once here and second time here. So this is not being shared properly. And then no neighborhood information, that is what is on the left hand side, right hand side, and then unlinked data require a large amount of storage memory. So since the data is not linked, it need to store all the coordinate pairs in the data structure, irrespective of whether that coordinate string is being shared or used. So because of that, there is a lot of redundancy in the data if you adapt this particular data structure. Then a whole polygon structure. It is also one of the structure. It is like a kind of spaghetti model wherein a polygon is described by listing coordinates of points in order as you walk around the outside boundary of the polygon. So coordinate borders for adjacent polygons stored twice. So here you have the same problem, and all lines are double except for those on the outside periphery. So there is no topological information stored about the polygons. So what are adjacency and common boundary, how to relate different this thing. So this is one of the example how you use this polygon structure. Now if you see this A, B, C, D, there are 4 polygons. E is another one, like 5 polygons are there. Now you have this X and Y. Now if you see this A starts with 3, 4, then it goes to 4, 4, then it goes to 4, 2, then it goes to 3, 2, and then again it goes to 4, 4. So 3, 4. So this is the way you depict your individual coordinate strings for a polygon. So you can see that you have a polygon wherein you have n number of coordinate strings. Now the same coordinate string you will repeat in B polygon like B 4, 4. But in A, if you see here also you have repeated this particular coordinate string. So similarly this will happen in this polygon also. So this is the way you store your data into the computer by using a whole polygon structure. Now there is another one called points and polygon structure, which is slightly better than the whole polygon or a spaghetti model, because here you are slightly removing some of the disadvantages of this thing. So polygons described by listing ID numbers of points in order as you walk around the outside boundary. A second file lists all points and their coordinates. So it solves the duplicate coordinate problem, that you don't have to again store the same coordinate pair as you stored in spaghetti model or in whole polygon structure. Now in this, lines can be handled similar to polygons. So you will have the list of IDs. So you don't have to separate both, and still no topological information. So still it is lagging the topological relationship. That is the adjacency and all. Now here we are storing the same structure by using a points polygon. Now here you see all these points as stored as 1, 2, 3, 4, 5, 6. We have 12 coordinates, coordinate strings. All these are being stored like this. And the moment I say a polygon, I will immediately say 1, 2, 3, 4, 1. So by this, I will not store n number of times the same coordinate string. So this is a little bit of optimization has been done in this particular file structure. Now we come to the most successful and the present structure, that is called the topology. Just to give you a definition, it is a branch of mathematics that deals with properties of space which remain invariant under certain transformation. Now you basically here we are trying to achieve all those lacunas available in the earlier structures. So I want to store the lines. I don't want to store the duplicate coordinate pairs. I don't want to store the duplicate lines. I want to have the spatial adjacency. I want to have the neighborhood information. All those things are is there in the topological structure. So the moment I say topology, it means I will have an area which will have a closed polygon. Contiguity means what is on the left hand side, that is I am taking care of the neighborhood, and connectivity means what is the starting node and the ending node. So like if you see now here, if I apply a rubber sheet transformation to this particular this thing, and it has transformed a lot, but my topology will remain same, because if you see the connectivity, contiguity, starting node, ending node, and the area, all these things are intact. Area may change, but the basic information about the neighborhood, all those things will remain same. So the topology basically says that whenever you apply any type of transformation to your map, it will always retain the same relationships. The only thing is, if I remove any of these arcs, then I have to rebuild my topology. So that you have to ensure. So topology, connection and relationship between objects are independent of their coordinates. Topological properties of an object are preserved when the object is stretched, distorted, and bended. So apply any transformation to a topological body, you will have all those three relationships intact. You don't have to bother about what will happen. But the moment if you adopt a different data structure, then you have to this thing. But if in a topology, if you remove any of the arc, if you change the connectivity, or if you change any of those things, in that case you have to rebuild your topology. Then overall major weakness of SData model is allowing for GIS analysis, like overlaying, networking. All those things are possible with a topological structure. Then requires all lines be connected, polygons closed, and loose ends removed. So all those things you have to make sure that topology